if an object moves in some manner, its velocity can be considered as a function of time. If I know how this ball moved, then if you give me a time starting with some event, I can tell you how fast it's moving and in what direction. It also has velocity that can be written as a function of x. If you tell me where, I can tell you how fast. So velocity can be considered to be a function of time, or it can be considered to be a function of position. And in some cases, we want our dependent variable to be time, that is, velocity considered as a function of time. In other cases, it's more convenient to consider velocity as a function of position. When this thing gets here, how fast is it going to be moving? Now, in order to get a handle on how this works, let's just take the expression m dv dt, which of course is mass times acceleration. Now, if we combine m dv dt, we can use the chain rule. If we take the expression m dv dt, we can apply the chain rule and interpose the variable x in the form m dv dx times dx dt. That's the same as m dv dt, so that this would be a perfectly good function to use for a force function. It's a mass times an acceleration. Now the key is that dx dt has an interpretation. You might think of what that is, but if x is a position function, dx dt is nothing but velocity. So that this is nothing but m times dv dx times v, or mv dv dx. And once more, this is nothing but mass times acceleration equals net force. So our net force can be expressed as m dv dt, mass times the derivative velocity with respect to clock time, or as mv dv dx, where v is understood now to be a function of x. If our net force is known as a function of position rather than as a function of time, then this is a very handy tool we can use. So we consider the advantages of considering f as a function of t versus f as a function of x. And you might say that's f net. Okay, if we know the net force is a function of t, then it makes sense to solve the equation m dv dt equals whatever maybe our constant force is minus kv. This would apply to the situation where the drag force is proportional to the velocity. Alternatively, if the drag force is somehow still proportional to the velocity, but our f is a function of position, then we might want to solve the equation in this form. We can recognize, well, let's worry about the form of the equation in a minute. I'll say if the equation was in this form where this force is constant, then this equation is easily separable, and we can get velocity as a function of x. If we use this, we can get the velocity as a function of t, and we'll look at some examples.